Yeah, so today we shall start on the basically this is the last few things that we will cover in the course, and this is the classic theory of diffraction, which I think you guys have done not in the way that it is treated in more advanced optics, wave optics. Says that you probably know that you've heard of Huygens principle. You have Fresnel. I think you've heard the names of Fresnel and Fraunhofer diffraction. Maybe you've just looked at how those work in the sense of at least you know that Fresnel means near field and Fraunhofer means far field and all that stuff. But I don't think you are quite aware of how this treatment is generally, the real math behind this phenomena. I don't think you guys have really covered. So what we shall do for the next couple of days is, well, I'm not really going to go into the vector theory of diffraction, which is really that is the real advanced stuff, because that sort of tells you, that takes into account polarization as well, direction of the electric field. What we are going to do is the scalar theory of diffraction, where polarization does not play a role. The vector theory is indeed what is much more interesting, and it reveals many sort of very interesting phenomena out of that. But the scalar theory itself is a good starting point as to how to, go about this. And in case people are interested, you can always look at. The initial part we'll be covering from Born and Wolf, which is the one book in wave optics which almost has everything. I mean, of course, very recent topics probably are not covered, but other than that, everything that you can think of in wave optics. I mean, the fundamentals, the basics, even the somewhat more complex stuff. Everything is covered in Born Wolf. So the first part that we'll do to find out, to establish the basic Huygens Fresnel principle, which lies at the basis of the theory of diffraction, in the sense that is how any diffraction problem is typically attacked. Okay, so what you basically want to find out how a field of light evolves in the presence of obstacles which are comparable to the wavelength of light. That is essentially what causes diffraction. But in order to know that, it is essential to understand how this theory actually works, in the sense that what is the real the math behind stuff that we shall use. So once we have that, afterwards the Fresnel and Fraunhofer are just approximations in the exponent. There's not too much of understanding there. But before that, I think it is important to understand how this, general addition of, so basically it's a superposition principle. So how the superposition works, that is very important to understand. So let me start sharing. Essentially, we will cover the Huygens-Fresnel theory principle, you can say, the Huygens-Fresnel principle of finding out. Uh, oh God, again this thing. This whiteboard just disappears. Anyway, so yeah, as I was saying, so
Presenting.
yeah, I want to present, but the thing is that the Huygens, my whiteboard just opts itself out in the options. I have to restart it. So I need to present again. Yeah. Okay. Here it is. Okay. So what we are trying to basically, 1 minute, let me just zoom out a bit. So the first thing that we will study today is the Huygens Fresnel principle. So basically, what the Fresnel was essentially the guy who really understood for the first time what this diffraction was all about. But what he did essentially was to use what this guy has done. This is obviously much earlier than Fresnel. So what Huygens, of course, said, and that you know that I guess quite well, that he gave first the concept of a spherical wave and a wavefront, and of course stipulated that every point of a wavefront gives rise to the secondary wavelets, right? And what Fresnel said essentially was that diffraction is nothing but diffraction was just adding these two together. Let me put it in a better way. Essentially was taking secondary wavelets and their superposition. I should actually go to this. Okay, the superposition of secondary wavelets essentially gives you the phenomena of diffraction. That is what Fresnel really sort of developed. That is the theory that he developed. So, what and what is important to what is this Huygens Fresnel principle telling you? What is that? What that basically says is if you have some kind of a point source, suppose that say some point p0, okay, and you want to find out the field at some point p, and this point p0 basically gives out spherical waves, okay. And what is so if you have spherical wave, then the envelope so on the that spherical wave, you basically define this wavefront, which is nothing but the points which have the same sort of a phase. If you have a series of spherical waves, you then define a wavefront, right? And so essentially, if you have things like this, then you say that I have this kind of a wavefront where everything is in the same phase. And this is like actually this is I should say this is a what one should technically actually say that what we consider here is any point source actually, it gives out spherical waves, of course, but the wavefront here actually is also spherical, right? So basically, if I just deem this, if I consider this to be, where is it gone? 1 minute. Yeah. So I should just not write it like this. So I think it's better to write this as a wavefront itself. So if you have spherical waves, then the wavefront essentially is like that. And then what Huygens says is that every point also gives rise to secondary wavelets, which are also spherical. And then so now think that this is like a point P and P naught, and you have some spherical, this is a point source, it gives out spherical waves. I construct a wavefront at some instant of time, and then I want to find the field at P. So this is how you do this, that the technique of doing that basically is then translated directly to diffraction when you have an obstruction in the middle. Okay, the first step, very importantly, is to find out how you will find out the field at a point P due to a a primary source or a point source at point P naught. That is the first problem. and that is essentially elaborating the Huygens Fresnel principle. Okay, so I will use this. So this part I think you should absolutely note. This is from Born and Wolf, and this is chapter 8. This is chapter 8. Okay, and I will directly use the picture advantage of online. So straight put this, and in fact I don't need to have my art. Don't need this big. Okay, so this is basically what I said. This is exactly what I want to do. What I say is that I have a point source here, P0. I want to find the field at this place, P, and say this. Okay, so then this construction I'm explaining at one in a second, in a bit. So what is this S? So this S basically, S is nothing but the instantaneous position of a wavefront. Okay, this is basically a wavefront at an instant of time t. Okay, so then clearly the amplitude, if I this is a point source and this is the distance, the radial distance from there, then the amplitude at B is clearly some, as is less like a spherical wave. Is just a k I this thing by r0, and you know that each element of the wavefront
So you mean
S
amplitude at Q?
amplitude at I sorry the
Q.
amplitude at B.
Where
No,
is
this
P?
is uh no wait. No, this is B. So Q, yeah. Oh, I wrote it. Yeah, sorry. This is Q, of course. So I should just maybe I just put this as B, and this is easier. I put this as alpha. Okay. So amplitude, yeah, this is of course. Oh no. So I was thrown out. Can you hear me?
Yes, sir.
Yes.
Yeah, I was. Hopefully, this will not be a problem again. Anyway, yeah. So this is what I had just said. I don't know how much you heard. So essentially, what I want to do is find out the field at P due to a very very small surface element ds at this B. So that is given, of course, by this so this is now the source of secondary wavelets. So naturally the amplitude here that emanates secondary wavelets here. So obviously what you will here have is some a e to the I k r0 by r0 e to the I k s, and this distance of course is s by s ds, and this is also necessary because remember this is finally some this is a field, right? So if this is a field, then again I mean, this ds has to be there. If you just think of this, because this is essentially this is if this is for the area element, this thing, this is, I mean, what you have here is just for a point source. So the moment you have a small surface element that is ds, then the field because of that will be just that multiplied by ds. Okay, now along with this there is a factor k of alpha, where this alpha is essentially the angle that this this distance, this s, that subtends with this this point on the wavefront from the source. So this is that point on the wavefront from the source, and this is again that due to that point, due to that secondary wavelet that is emanated from here, the distance that comes here. So that is the angle that this subtends. Now, so basically, because you see, so you can understand that this is sort of radiating outwards, right? So obviously, uh, what this k alpha does is kind of it describes the variation of the amplitude with respect to the location of the secondary particular secondary wavelet or that point on the wavefront which we are considering. Okay, is that understandable? So what I'm saying is basically this k alpha is an angle, is some kind of a factor, some kind of uh, 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 geometrical factor, you can say, but which is kind of describing the variation of the field here due to the particular location of the secondary wavelet on that particular wavefront I'm considering. So what you can envisage is that this will be the maximum contribution will come when that alpha is zero, when this distance is minimum, right? And the minimum will be when this is almost tangential to this, when this angle is basically tangential, when essentially when the alpha is pi by 2. Okay, now the task of course will be to find out what the value of this alpha is. Okay, that is very important. So I'm finding out at the moment, the approach is we are finding out the field at p due to a small surface element, this ds, and then of course we will integrate over the entire spherical wavefront in order to sort of get the total field. Okay, so now so let me just write this down. So essentially this is an inclination factor which describes describes the variation of amplitude variation of amplitude of the secondary wavelet as a function of direction with respect to p. Okay, so how this amplitude is varying as the location of the secondary wavelet is changing with respect to p. So, for example, if you look at Miloni and Everly, they do not, they have that factor, but they do not explain why it is there. They just tacitly say that it is there in Born and Wolf, go and consult it. Okay, so I think it's better to follow the entire process that Born and Wolf does. So, anyway, so as I said, K is maximum at alpha equals 0, and it is 0 at alpha equals pi by 2. Okay.
Sir, what is that quantity U?
So this is essentially this is the field at P. So this is the the element, the, okay, sorry. This is the field at P due to surface element ds. Okay, so ds is on this source, on this wavefront. Okay. So I think I'll
Sir,
zoom in once.
DS is what?
So ds is it is just a surface element on the this thing. So it is basically a surface element at S. Okay. So
Oh,
what we
oh,
are trying to, oh, understood, na? So this is just a surface element on this thing, and then we integrate over the. We just do a basically a double integral and then get the total field. That is quite obvious, but how you will find out? So this the interesting part is how you will basically, so see, we want to account for each of these regions, right? All the wavefronts that are here, we basically have to account for. Okay, so that is the trick that sort of Fresnel used. You want to, this is the, so the problem in Huygens is that he says that every point is a source of secondary wavefronts, right? So then how do I understand that, right? So what is the meaning? How do when I put that as some kind of a math? Okay, so that is what he was trying to basically develop. And the construction was quite ingenious. So what he said was, so he basically made these Fresnel zones. Okay, so these that you see, these sort of arcs of a circle, so these are nothing but Fresnel zones, and these are basically drawn with radii B, this, so first one, that is tangential to the wave front, that is having a radius b from the, so field where I want to measure the, from the point where I want to measure the field, right? And then each of these, then subsequent, these are called Fresnel zones. These are differ by lambda by 2. Okay, so that is the genius. So then so you basically find out uh, the so you uh, basically find out the field due to sort of each zone. Okay, so
sir, what differs by lambda by 2?
so basically, okay, let me just write this down. So let me just first write down that the total field, so the actually you can just write it here itself. So the total field at P or UP, that is some A E by R0. And this is of course HE by K R0. And this is a surface integral of K alpha, sorry, E I K S by S K alpha ds. This is the total field. Okay. Now let us describe this Fresnel zone. So what I am saying is, so basically, this is nothing but uh, so you so yeah, so basically you just construct a series of circles, you can say spheres. Okay, and the radii of the spheres are, it starts from the minimum, the minimum distance. So think of this, Hitesh. So each point here of this spherical wavefront is actually varying in distance. Now that is the main problem of finding out the field due to each of the spherical wavelets. That is the basic problem, right? So what he does, he actually constructs spheres from here, spheres which intersect different points of this wavefront. Okay, and these, so Fresnel constructed spheres which intersect the wavefront S at intervals of the successive spheres, intervals of lambda by 2. That is really nice. So basically what I'm saying is that the sphere with the smallest radius is B. The next one is B plus lambda by 2. The next one is B plus lambda. B, the 2 lambda by 2, that is then the one next one is 3 lambda by 2. 4 that you just continue. Okay, so these are very, very close to each other. Okay, and then what he does, he basically tries to find out the field due to each zone. He basically adds up. He finds out the field for at P for the jth zone, and then adds up all the zones. Okay, to get the total field. You understand? So the basic thing is he constructs. So how does he measure the field at P due to all the points in the secondary, on basically all the secondary wavelets on the wavefront? He basically just constructs. So and the why is that being done? So the and the whole thing is that this B and this R0, okay, these are both much larger than lambda. So what he assumes is that the variation of that inclination factor along the whole zone J is the same. Okay, so he ascribes a single kj for each j, and then you know that for each j you have an expression like this, and then you basically, if you know it for one j, you just add all the kj's, I mean all the j's, and find the total field. Okay, so basically that means that I have the first radius is b, then b plus lambda by 2, then b plus 2 lambda by 2, and these are essentially this z1, z2, z3 what I have here. Z1 is b, so let me write down, this is z1, that is z2, that is z3, like that. Okay, so okay, is that clear? Was a very, very interesting construction that he did. So basically,
So
what we are
at B we get a contribution just from single point, but at
from, yes,
B plus
correct, correct.
lambda
So
by
then you
2
are,
we
yes,
get
yes. B is
contribution
for a
from,
single zone.
yeah,
Okay.
from the
So
region
basically,
between
B,
Z1 and
yes,
C.
yes, yes, exactly. So
Okay.
B is corresponding to a certain zone. So here it will be this Z whatever Z4 or something like that, Z5 or something, whatever, something like that. Okay. So since R0 and B are both greater, much greater than lambda, so K has the same value Kj for for J zone. That is the very important. So see, you really understand, yeah. All of you just note this. Physics finally is the science of clever approximations, which give you the correct answer. जब वो कर पाओगे ना, you will really become a great physicist. I mean, see, there are all, this one is brilliant. I mean, I really love this derivation of, the way, see, because you understand the problem. It's very non-trivial, right? So Huygens just said that you have spherical wavefront. All spherical wavefronts say you have, every point gives you secondary wavelets, and now you, okay, fine, figure, go figure. I mean, it's bloody complicated, right? So there can be infinitely number of wave fronts, and how do you finally find out the field that due to all of them? I mean, the way this Fresnel has, done this is see really very, very interesting. You just appreciate it. So basically, okay, let us continue with it. So now what he does is he says, so see, I need to essentially get that integral somewhat, I have to solve this integral, right? So that we have to get into some form which is doable, okay? So what we are saying, what he uses is just the triangle law. So there are these three sides of the triangle, right? So this is S, that is R0, and this one is your B plus R0, right? So you use the cosine law of triangles, and you will get this S square. If I write, so basically is R0 square plus R0 plus B square minus 2 R0 into R0 plus B cos of theta. Okay. So then what is your this thing? Then very clearly you have, let us just go up. What you have is your S. If I take take the derivative, taking derivative, you have SDS as R0. Just so it's basically now we are taking it, out of these are all constants. Only thing that varies is basically theta, right? So you have just your R0 and 2s ds, ये 2 cancel हो रहा है, R0 plus B sin theta d theta, right? So basically I will write this down in terms of now theta and phi, okay? And your theta is also obviously this one that is given here. This is theta. अच्छा ये थोड़ा छोटा हो गया ना, this one, इसको थोड़ा बड़ा करते हैं. Is this too small? Anyway, you guys can see this, right? You can zoom in and see probably later on. Anyway, so theta is obviously clear. Let us start a new screen.
Sir, how do we know that under that approximation, that R naught and B greater than lambda, then K will have the same value for all J's?
Now that is an assumption that R0 and B are much more than lambda. That of
But
course is
how
the,
do we know
to
that that
see.
is a
Remember, this is scalar diffraction, and this is also not. I mean, going under the. I mean, yeah, we are not really looking at sub lambda distances. Okay, we are looking at things much bigger than lambda. I mean, the basic construction of Huygens was this. Okay, and what we finally see, I can only tell you, Hitesh, that the basic, the superposition principle that he gave has so now you will agree that if you assume that R0 and B are more than lambda, then that K is same, because that is so large, that sphere, that circle is so large with respect to lambda, the difference, that you can assume the K is to be same. I mean, the curvature is very extremely small. Okay. Now the flow of logic that I can tell you is that this is the basic superposition principle that helps us derive the expressions for Fresnel and Fraunhofer diffraction, and those absolutely agree to what you get with experimental results. Absolutely agree. I mean,
that is fine, sir.
huh, so that is the only reason I can tell you. I mean,
When
we
you
assume
say
that they are more than
the
lambda. If you
curvature,
don't assume, it becomes infinitely more complicated.
yeah,
Okay.
so when you say that the curvature becomes very small, is it that the wavefront appears to be almost a plane wavefront?
Now, curvature small, na curvature large. I mean, it's almost like a very large. No, so no, but remember, this is again, Ritesh. It is not the wavefront. This is a construction I am doing at a direction opposite to the wavefront, right? Because that wavefront is that spherical wavefront. See, I am basically making these the I'm so Fresnel. I didn't do Fresnel did of course. Fresnel basically was trying to find out the contribution of each point on the wavefront. So he said that एक point नहीं करेंगे, we'll do different zones, and I'll find out the field due to every zone. And then the trick I use is that the difference between one zone and the next zone is very small. That also we will use later. And doing that, he came to this expression. And once he comes to this expression, we basically see that that is what we exactly use in diffraction theory when you want to find out the field at one point in space and how the field evolves at a different point of space, assuming all are spherical wavefront. And then we have this, the conditions for Fresnel diffraction, for Fresnel, that is the so-called near field limit, and the Fraunhofer, which is the far field limit. And whatever you experiment you get do, I mean, we will also do the circular aperture, and it is absolutely fantastically, it matches what you get. So obviously this means that if you the consideration that lambda is much smaller than this, I mean, this construction of assuming lambda to be much smaller than this thing, are those, the distances involved here, that is small. And I can only say that this theory will not work when I am trying to evolve, I mean, find out the field at distances closer to lambda. There of course you can say that the wavefront is almost the same. I mean, it is very little change. That also you can say. But of course, nano optics is a different thing. You have many much more issues come. But essentially, what we also know that the diffraction. In fact, you can say that this is, I don't know whether this is saying too much, but diffraction basically tells you that there is an uncertainty of lambda. Okay, that diffraction limit that we say, na, I mean, for example, that is the reason why when you focus a plane wave using a lens, I mean a Gaussian, or anything, a plane wave using a lens, you don't get a point, you get a spread. So maybe that uncertainty is lambda. Within lambda we cannot talk, we cannot even talk about. Okay, so whatever we are thinking, yeah, I think that is the best answer. This entire construction of diffraction with plane and spherical waves relies on the fact that we are looking actually at distances which are more than lambda, which are not infinitely, I mean, which are obviously, if you have a, you look at obstructions which are, completely, I mean, or openings which are like very unbelievably large, or it's a window or something, you will not get diffraction because of that. But at even with that, given the fact that lambda is finally of the order of less than a micron for visible light, we are certainly looking at distances more than that. And indeed, we cannot talk about anything that happens within that. Our uncertainty is lambda. See, that is why there is this diffraction. You know that the when we say that the diffraction, that plane wave, I mean circular aperture, say when you have a plane wave going through, right? So then the radius of the spot is the Rayleigh criteria, whatever we say, right? It is essentially 1.22 lambda by d or something like that. So that lambda is a figure that we cannot, get past. So that is what I can say. So we don't look at distances which are comparable, completely same as lambda or less than lambda in the diffraction theory. It doesn't, it breaks down. Okay. Anyway, so let us continue. So Huygens, Fresnel continued. Okay. So basically we had, again, let me write down. This one was S square equal to S square R0 square plus R0 plus B whole square minus 2 R0 plus B cos theta. And then from there we wrote your ds is R0 plus B sine theta d theta. And then for the, and also you have your uh, ds in terms of your the surface element volume. We know that the surface element basically area is given by R0 square sine theta d phi d phi, right? Which can be written from here, from this geometrical consideration. We can write that as r0 by r0 plus b s ds d phi, right? So just the sine theta d theta, we are basically writing like this, right? So then for the jth zone, I mean the sine theta element, we are replacing from here, writing like this. So basically that means for the your this thing for the jth zone, uh, for your jth zone, you have this uj of p, that is just phi mein to it is that is complete, symmetrical. There is no, it's just 2 pi in the phi. Theta is the one that is really varying. So I k r0, r0 plus b, and basically I will integrate between b plus j minus 1 lambda by 2 and b plus j lambda by 2. This is the contribution of the jth zone, e to the I k s ds. Let me see if I've got this correct. Yeah, kj I have missed, no? kj kj. ठीक है? This is right, no? From the thing before?
Sir, it should be 2sds on the left hand side.
No, 2sq.
Oh, no, sir. The one on the second one.
This one.
Second. No, sir. The second
This.
one. Yes.
Oh, yeah, yeah. No, no, no. I'm cancelling off ना. STS. No, no, STS. 2 cancel हो जाएगा ना, इसमें 2 है.
Will cancel
2
sds.
cancel हो जाएगा. Right. अच्छा, ठीक है. तो then this is basically very simple. This will be if I integrate, ये तुम्हारा आएगा minus I. So ये थोड़ा, yeah, so क्या e to the I k s by this thing. So this is minus 2 pi I by k a e I k r0 r0 plus b kj kj, and then this is essentially e to the I k s का तुम्हारा ये जाएगा from b plus j minus 1 lambda by 2 to b plus j lambda by 2.
So where
Okay.
did phi came from?
No, this is the two-dimensional ये element, na? No, this is basically not. Don't continue confuse from here. Okay. So this is basically the two-dimensional surface area, the element that we have. No,
Oh, that is different. Is
that is different. इससे मत confuse करो. अरे, this is just the classic
so the
thing that
two
we
s are
have.
different.
हाँ हाँ हाँ.
Oh,
Completely
oh, I
different. This is the typical volume area we have. So the
okay.
typical area element in spherical polar coordinate. And is it a constant? So we cannot integrate over r. We are only integrating over phi and theta. So phi it is symmetric in the azimuthal direction, just 2 pi. Theta is the one that is varying. And theta we replace from here, basically. Okay. So basically from here I am getting this thing. So I don't know, maybe it is, yeah, but then there also I wrote that ds, no? So that is why
The
this
two
is
s
like
are
I wrote.
different. I mean,
Kind of different. But this is the
they are not.
classic surface element. So this is the
Yes.
one that we had in the integral. इंटीग्रल में जो था वो पहला
Yes, sir.
पेज में, उससे
Yes.
उसको हम ऐसा लिखे, then from here I got this. This is
Now
just
I
a
got.
distance. This is just a
Ha.
maybe we should put this as small. Okay,
Yes. Ha, that will
small
be
is
better.
that is better. Okay. So उसमें भी I will just change. So उसमें भी I will put small s. Let me wrap this properly and write s ds. Good. So उस page में भी also we have to write. So this is all small s. Okay. Okay. तो ये अगर किया अच्छा तो ये थोड़ा इंटीग्रल करो ये क्या आता है देखो दिस इज बिट कॉम्प्लिकेटेड आई मीन कॉम्प्लिकेटेड नहीं মানে essentially this is going to come as something like this part মানে just this part I think this comes as तुम्हारा e to the I k क्या है k b plus j lambda by 2 या b plus j lambda by 2 into 1 minus e to the minus I अरे यार e to the minus I lambda by 2 ऐसा कुछ आता है right I think that is what
minus
comes
ik.
I k yes you're right yes very good thank you I k हाँ so then तुम्हारा total integral इसको मुझो so the total integral basically will come as uh, minus 2 pi I by k then a e to the I k r0 plus b नीचे r0 plus b तुम्हारा यहाँ पे e to the I e to the I k j lambda by 2 1 minus e to the minus I k lambda by 2 right and acha so this part will be k lambda by 2 mane this is 2 pi by lambda so this will be just e to the e pi j right so this part will be e to the I pi j 1 minus ये है e to the minus I pi right this part 2 pi by lambda lambda cancels all cancel e to the minus I pi और minus e to the minus I pi का value is basically this thing right so minus 1 right just
Sir,
cos
if
pi
all
sin pi
if
0
all the k are equals to 2 pi by lambda, then what's
hmm.
the point of this index
hey
j?
kj अरे यार oh, I am completely confusing you with the this is very different. Let me write this as small k.
Sir, that
This is
kj
the
is the
geometric
inclination
factor,
factor.
inclination
Ah,
factor that has
oh,
nothing to do with wave vector.
okay, okay.
इसको सब बदलो. Oh, this Born and Wolf का notation is the problem. They have used this. Please, this is big K, this is small k. This all, अरे यार. Let me make this all small k. All small k. Small k. Small k. कहाँ पे k है? Small k. Small k. All are small k. These are all small k. Big k. This is small k. Okay. So wave vector and inclination factor are completely different. Nothing to do with each other. Okay. So then basically what we have, ये given that e to the minus I pi मतलब minus 1 to the power of j, ये j है. So at the end we can write down this as minus a minute, yeah. So minus 2 pi I, no, एकदम final expression let me write. So this is 2I lambda minus 1 to the power थोड़ा please check करो kj e I k r0 plus b r0 plus b थोड़ा check करो इसको I think this is correct hmm? Is that correct थोड़ा चेक करो.
Yes, sir.
Okay, then तो great. Then this is my this thing. Then my u p is just 2 I lambda a. अभी main challenge आएगा e to the I k small k r0 plus b r0 plus b अभी j equal to 1 to n minus 1 to the power j plus 1 kj. ओके, तो इसको क्या कैसे, हाउ डू यू फाइंड द वैल्यू ऑफ दिस, पता है इसको कैसे फाइंड करते हैं? दिस इज अ फेमस मेथड ऑफ डूइंग दिस. किसी को पता है? सो बेसिकली यू कैन अंडरस्टैंड दैट इसका कैसे आएगा. दिस इज जस्ट गोइंग एज सिंपल, राइट? दिस इज k1 minus uh, this yeah, so k1 minus k2 मतलब j equal to 1 मतलब square my plus k3 minus k4 करके 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 this is basically plus minus of 1 n to the power 1 kn, right? So how do you find the value of this series? Can you approximate it by some method? हाँ, अनिरुद्ध और हितेश, रोहन, पता है किसी को how you do this? There is a way of finding out.
Sir, I think we can do something like separating in even and odd.
Yeah, so basically Schuster's method. Okay, let us do that. Huygens Fresnel continued. So basically what you have is तुम्हारा minus j equal to 1 to n minus 1 to the power j plus 1 kj, right? So अभी जो the standard Schuster's जो method उसमें है, so basically you, I mean it's a very, again it's a complete game of approximation. Okay, this is not an exact method, but this is a very clever method, that I must say. तो Schuster's rule में क्या होता है? So obviously n odd n even होता है. So you basically consider two situations. Okay, so the situations that you consider, one is that the k your so consider the situation where any kj is greater than the arithmetic mean of the number that is just before it and that is just after it. Okay, I considered this situation. हाँ, तो ये situation अगर लिया, so then they this basically will be माने I can write down this तुम्हारा जो है था. So this was what, this was k1 minus k2 plus k3 plus minus k4 ऐसा जा रहा था, right? So I can write this down first in this kind of a manner. K, I write down this as k1 by 2 plus k1 by 2 minus k2 plus k3 by 2 plus k3 by 2 minus k, अरे यार क्या लिखा, k3 by 2 minus k4 plus k5 by 2 plus k5 by 2 ऐसा ऐसा करके minus k6 plus k7 by 2 ऐसा I can write. हाँ, तो इसका लास्ट टर्म क्या होगा? When for n equal to odd, if I write like this, लास्ट टर्म क्या होगा? हाँ,
kn minus 2 by 2 minus kn
no,
minus 1 plus
this
kn by 2.
Yes. But interestingly, Anirudh, see, what can you conclude about all these, given I have this?
They're negative.
Yes, exactly. So when n is, so if I branch into threes, into these three numbers like this, then for n equal to odd, I will only have this left, right? And for n equal to even, I will basically have half kn minus minus 1 minus kn. Can you check that out?
Yeah, that would be it.
That is right, correct?
Sir,
Huh?
Yes.
why did we consider this situation where the middle number is greater than the mean of the
I will
previous?
consider, Rohan, two types you have to. Once you considered that, other time you considered the ulta.
Okay.
Okay, either it will be this or it will be that. I mean, no, and it's so big. So
It can be equal to.
see, the whole thing is, if it is, I mean, if so, basically, what we will do is, what we want to do is, we will write down the series also in such a way that this is like that. Okay, so we will, you can say that I have the sort of a finite time series, not time series, some kind of a series. So if there are problems, then those come as errors. Okay, so anyway, so hear this out. What we can, let us just finish this before we go into its pros and cons. So see, the moment I have this, when all these are negative, then I can safely say that your तुम्हारा this one sigma basically is less than less than k1 by 2 plus kn by 2 when n is odd. That is fine, right? Because all these are negative. That means these, if I take them to the left hand side, so sigma plus those is k1 plus by 2 plus kn by 2. So sigma has to be less than that. And in the other case, sigma is less. If it's even, then sigma is basically less than k1 by 2 plus kn minus 1 by 2 minus kn. N is odd. Okay, so this you agree with, that if I have like this, then this is fine. Okay, so what Huygens did, the other next construction is that you write down sigma as, instead of what the way I wrote, like this, k1 minus 2 minus k2 by 2 minus k3 plus k4 by 2 minus k4 by 2 minus k5 plus k6 by 2 minus ऐसा, right? So इसमें क्या होगा इस पे? So when your n is odd, n is odd, so last term will be basically uh, yeah, minus half kn minus 1 plus kn and odd, and half, no, minus half kn when n is even. Somebody was saying something.
No, sorry. This only.
Yeah, this is fine, right? So ye kiya. We were saying the answer. That is correct. So now, Anirudh, you can understand the trick, right? So the trick so now these are all positive, right? So I mean, in the sense that this is negative,
So
negative,
we'll have
negative,
so
negative.
we'll have
So
summation less than that and greater than
yes,
some.
Akdom. So basically sigma is now greater than k1 minus k2 minus kn minus 1 by 2 plus kn when n is odd and greater than क्या बोलता है ये जो लास्ट वाला खाली K1, अच्छा ये क्यों गलत नो है, करेक्ट, हाँ राइट, K1 माइनस Kn/2, Kn/2 when n is even. Okay. So now Schuster's, or rather, yeah, Schuster argument basically is that it's just a bit, yeah. So basically, the thing
Average.
is that these are very close to each other. Okay. I mean, the general argument that so basically each kj, they differ from the neighboring values kj-1 and kj+1 actually very slightly. Okay. So then what we are saying is that the right hand sides, so basically these and these, they are almost equal. So the argument is that since kj is differing rather, is differing only a little from kj-1 and kj+1. Basically, what we say is that when this is even. Sorry, yeah, bologe to is even, right? So what we tend to say is that ये case, ये और ये these are very, these are similar. Okay. And then what we basically get, so then basic what I'm trying to say, what the law, I am not saying what this guy basically said, what Schuster's method, was Schuster's argument is that ये इससे less है और इससे greater है, so these are all very close to each other. So and same for this. So his argument is that sigma is almost equal to k1/2 plus minus kn/2, where this plus is for odd and minus is for even. Okay, now you might have issues here, but this is a very standard method. Okay, a very standard method that is done, which all actually agrees to most calculations like this, and one can absolutely check, Rohan, if you now reverse that, ki kj is smaller than the arithmetic mean of the the two neighbors, then वो just उल्टा हो जाएगा, एक पॉजिटिव पॉजिटिव हो जाएगा, and again the same thing will happen. माने the argument will still remain, वो just कैसे लिखो, माने it will reverse the way I did, उसका उल्टा करोगे तुम. So basically the problem happens, as what you were saying, is that when some of the terms, bracketed terms, so see it is perfectly fine when all the bracketed terms are the same sign.
Sir,
Okay, but huh,
did you miss a term in the sigma greater than for even?
uh, which one?
Should it be
Yes,
k1 minus k2 by 2?
this
अच्छा,
one. No,
no
no,
no
ये
no,
ठीक है.
greater than वाला नीचे वाला.
ये
The k2 is not
K1,
here in the second one. The
K1,
e,
oh, so yeah, the K2/2 होगा. Sorry, you're right. ये
and even the
हाँ, ये
one below it.
obviously right, ये होगा ना, ये है ना,
Even the
K2
one below it,
obviously.
like नीचे वाले
हाँ,
grade,
इसमें भी K2/2 होगा. Yes, I
and
missed
then
this.
minus k and
ये प्लस होगा ना.
be separate.
हाँ, this is okay, no?
K1 minus k2 by 2 and minus.
Minus Kn/2.
There will be three terms.
हाँ, 3 of course, yeah, I know. Boy, no, this is obvious, right? यहाँ पे दो है, right? So this has to be there. I missed both. Minus k, obviously, right? यहाँ पे जो रहेगा वही तो. These two are not in. So whatever is in bracket, those are not considered. So whatever are not in brackets, those are the things that we consider. Okay, so no, not in bracket matlab जो बने. So in case of
and,
odd,
and a
not
by
in
2.
bracket is this,
Kn
and
by
ये by 2.
uh,
Yes, correct. So yeah, as I was saying, Rohan, the problem happens when you have a mixture of odd and even. Okay. So I mean, in the sense that, as you said, it is not necessary that they are going to be, all of them. I mean, the arithmetic means that chota hoga ya zyada hoga. It may not be that, but in the sense that, uh, if that is happening quite a bit, then there is, like, you have a lot of error terms coming in essentially, and then this validity gets somewhat compromised, in the sense that तुम्हारा bracket के बाहर बहुत सारे आ जाए, you understand, right? Here they are all same sign, and here also they are all same sign. If there is a case where there are some minus and some plus, then I mean, basically, error terms will, I mean, you cannot, it becomes more and more. So, suppose I'll tell you, suppose there are, you know, 10 negative and 3 positive, okay, terms, then you can still say that the negative terms are more. So, I can still write a statement like this. But if they are all similar, then of course this fails. Then definitely it fails. But as I said, experiment is finally God, and that works. Okay, that perfectly works. I mean, works money. This actually agrees very well to experiment. As a result of which, we nicely use this. So we basically write down the total field as just I lambda k1 plus minus kn a e to the I k r0, I k is like that, r0 plus b by r0 plus b, and now kn. So kn is the largest term, right? So the largest term, so kn is the largest angle, is for the, rather, is not is the, kn is for the largest angle alpha, and that tends to pi by 2, which means that kn tends to what? Kn tends to क्या? For the largest angle, pi by 2 जब होगा, when you are at perpendicular, so that has no contribution, right?
0.
0, right? So therefore we peacefully write this up is I lambda k1 ae I k r0 plus b r0 plus b. Now the final thing was that if this thing here, sorry, this thing also, what you have here, that also should be like a spherical wave, in which case this k here for this to be like a spherical wave, obviously this part has to be 1, right? So what Born and Wolf, I'm sure, our Fennel argued was that k has to be minus, ah, what is happening? I'm sorry, minus I by lambda. Okay, so this one is a argument which, yeah, but which is, I don't know. I find, I think whether some historian writes it, or whether actually Fresnel derived all this and then finally came to the conclusion that, this basically, this whole construction, after all taking all this, he finally came to this conclusion that, the inclination angle has to be, minus I by lambda, not I, sorry, this inclination factor. I mean, now this is no longer really an inclination factor, right? I mean, this is clearly something strange. I mean, this is imaginary, this is like an imaginary number, and this is telling us that, this I mean, I mean, the fact that we want this to uh, uh, be uh, in sort of this in agreement with what we typically should expect for the theory to be, then this comes like this. So after we come here, we actually realize that what Fresnel meant as an inclination factor actually turns out to be a phase. And why is and because, so beautifully, guys, just see here, this is K1, right? K1, sorry, K1, right? So you are appreciate that this is E actually nothing but e to the minus I pi 2 pi lambda. So what is this telling you? This is telling you this is something very interesting. So I mean, I find this really marvelous. See, think of this. Physics wise, this is now telling you that the secondary, the field at that point P, or rather you should say, so this is basically becoming because of the secondary wavelet that is starting off at that first zone, which is that that this one, that the one that ऐसा करके जो ये वाला था, right? This properly. So ऐसा था, and then this was the zone, right? So this is the first zone. So this was K1, right? So basically it is telling you that the secondary wavelet that emanated from the primary wavelet is actually having a phase difference of pi by 2, and it is the amplitude is falling off by a factor of 1 by lambda. That is really different. I think it's marvelous, right? He was basically, but at the same time, inclination factor is not really an angle. What we were trying to do is to find out the amplitude at the field, where a point where we try to calculate the field, the amplitude due to the angle alpha, or that zone J, whatever you say. Okay, so therefore, get that idea out of your mind, that that is something to do with an angle. That is actually an amplitude which is due to that certain angle. Okay, and that tells you beautiful, that really, but in a very startling manner, that this implies that the secondary wavelets have a pi by 2 phase lag from the wavefront, and the amplitude falls by 1 by lambda.
So,
That is very crucial. Huh.
you said the amplitude falls by 1 by lambda, but if you
Yeah.
substitute k1 as e power minus I pi by 2 by lambda, the
Hmm.
lambda will cancel, right? The u of p
Now,
is
but
equal to,
see that, yeah. So yeah, that is the total field, right?
okay.
Here we are trying to say that you are, so K1, if you think of it, that is
Okay, okay.
actually what is coming out of this, na? So that one is basically falling off by
So
1 by lambda.
that is
Yes.
just the first zone.
Yes, 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 something like that. Yes, yes, yes. So yeah, so amplitudes of yeah, I mean, it is falling like a factor of 1 by lambda. So see, but then at the same time, Rohan, if you think of it, see, one thing. See, okay, very no. Let us go by this. So if we went by, no, I think no, that is not correct, Rohan. Actually, it is the whole thing. See, think of it. We basically found out how did we come to this UP. We came to this UP by adding the contribution of each wavelet, right?
Yes.
Just we found the contribution of each wavelet and we came to this. Now we are saying that this factor actually, so if we just had the unchanged, then this would have remained, this would be
Sir, your voice is breaking.
I think sir left again.
He's here, but probably his internet is not fine.
No, no. I think that's the screen. Like when you share a screen, there's two of you. I think the voice went.
No, I can see him, the other screen also.
It will leave soon.
Guys, hello.
Yes,
Yeah,
sir, we can hear you.
yeah. Oh God, it threw me out again. Yeah, so I don't know how much you heard. So basically, I was trying to say, did you see this drawing? Yeah, so basically, what I was trying to say that when I have, so basically, I am having this point source here. I'm trying to find how the point source, how this the wavefront that is emanating here at any point of time it is like here, and then at each point of the wavefront we assume spherical wavelets are being emitted, and then the effect of each spherical wavelet I'm adding to find the field here. However, independently we demand that the field here also has to be a spherical wave. So that means the total field that I am getting out of the superposition of the wavelets has to be in the expression of spherical wave, give the same expression of spherical wave. Now, this, if we have this factor, there is a problem, I lambda k. So therefore, I insist that this has to be I by lambda, which means that the amplitude of each spherical wave actually is down by 1 by lambda.
Sir, so by getting all the adding all the contribution at P naught here,
P not, sorry,
uh,
P, P not नहीं, ये P है, वो
I
P not.
think you reverse that.
Yeah, ये उल्टा किया, yeah.
So
Sorry.
at P
हाँ,
we add all contribution and we got this U of P. In
yes,
this
yes,
expression we just have K1. So by
yes.
demanding that this is a spherical wave, we get K1 as
As that, yes, correct. But
minus
then
I.
that is an independent demand, Rohan. That is an independent demand.
Yes,
I'll
that is
say,
fine.
huh? Yeah,
My
yeah.
question is, we just
Huh,
found
huh,
out
huh.
that K1 follows this behavior, which is minus I by lambda. How do we
Yes.
know that all other K?
अरे because the final expression ही तो ये है. Final expression तो हम लोग यही निकाले. समझे? वो पूरा ऐड करके तो हम लोग यही बोल दिया. अरे, see, that was the whole trick, right? We were finding out the effect of everything, right? And
Yes,
then we saw that the total sum of all of those is actually K1 plus minus Kn. It is actually sum of all of those zones.
yes, that is
And
fine.
Kn is 0, so chala gaya. So then it is actually taking into effect all the wavelets only, na?
So
See, understand?
that I understood, but I don't
Yeah.
understand. Just by getting the value of K1, how do we conclude that
The
all other?
key one, see, Rohan, finally that is the answer, right? So
Okay.
that is the answer. So the answer tells you that there has to be a I by lambda, this thing.
Hmm.
Okay. Now that I by lambda is coming because I am saying that the net amplitude of all the spherical waves have to be multiplied by a factor of 1 by lambda, and there is a phase shift of pi by 2. That's अभी तुम उसको खाली k1, so basically you're telling you I'm saying that वो k1 का क्या होगा बाकी का भी सब सेम है.
I don't understand
Basically
how.
that is the thing
Yeah.
that we are trying to say here, but yeah, but you will admire, yeah, this is a fantastic calculation, right? I mean, I it was genius level actually, because I don't know whether they really figured out the experiment see one thing, for example, atomic physics, all the experiments, almost everything in the theory was done because the experiments showed that the theory was wrong. So yahan pe I don't, but then they do, I don't think they could really take light and find out the intensity distribution then, right? How will you determine? That is, there was no detectors then, na. So uska wo sync function nikal ke, then whether he found out this theory, I don't know. But this is brilliant. I mean, just think, just coming to this result by calculation, I mean, it's really quite mind blowing, right? I mean, see, you can always say that, "Arey, kaise kiya? How are you assuming that all the geometry, I mean, the arithmetic mean is going to be small, the whatever." But think of this, which of theory Fresnel finally laid down. I mean, that obeys any damn experimental thing measure perfectly. But and you would not have guessed this, right? I mean, this theory I really consider as brilliant because cannot. I mean, see, you understand the challenge, right? Because you have a wave front, each damn point is giving you a spherical wave, and you have to get the effect of all of them, right? And that he could manage to, finally get into such a beautiful small answer. This is really magical. I think this is one of the most interesting things that I probably we cover in this course. I don't know whether you will agree with this, but I find this quite phenomenal. I mean, there are ek ke baad ek assumption we make, but then all the assumptions turn out to be fantastically. So that is what I really want to know, whether he knew the distribution first and then figured this out, which is very unlikely, I think, right? Because well, Fresnel is like, I think, what, 18th century or something, na? 19th century, I guess. So that time, how could they measure that sync function? I don't know. Anyway, so I don't know. I hope you guys are also, you like this as I do. Yeah. So ज़्यादा थोड़ा time भी हो गया आज. So next class we will just use this formula, find out the this thing, Fresnel Fraunhofer thing, the relationships, I mean the factors, and we will also look at the plane wave, circular aperture. Very simple. That is extremely easy, and that will officially wrap up the course. That is what we covered last year, and then but then Friday maybe I will do a bit of optical trapping because that is what we promised the first time. Okay, okay. So yeah. So any more questions? Anything else?
Sir,
Okay. Yeah.
you took the values of k from the angle of alpha equals to 0 to alpha equals to pi by 2,
Yes.
but why did not you go beyond that?
No, but after that it is going behind. No,
Behind, so
man,
is there
behind
any such
matlab kya, it is going out of the plane completely, right?
Yes, that would be the on the other part of the sphere,
Yes,
but
that we are not. It's only forward propagating, right?
is there any such proof that the backward propagation is
No,
not?
but again, no, but at the same time, Shubhranshu, you have to think that my point where I'm measuring, that is for only the front propagating wave fronts, right? I'm measuring only at that point. I mean, the ones that are going backwards, they are not going to my point where I'm measuring at all, right? Because it's spherically expanding, na? The ones that
Yes,
are going, so that will
Sir, we are
measure in
still
the other
making an
way.
assumption here, though.
yes, we are assuming the directionality of the wave
Yeah.
propagation,
Of course,
Yeah,
but
of
because
course.
according to the
Yes,
Huygens secondary wavelet
yes,
theory,
yes,
the
yes.
backward propagation is also possible.
But
That is the
unless you have a
core question.
medium, how will that propagate? In the sense that you don't have a reflective medium or something. I mean, you just have a point source and everything is emanating outwards, right? So unless you have some reflection or something, why will it go back?
sir, if you have a
But
particular like a spherical wave,
Hmm,
let's say at some particular point P, and now
hmm.
according to Huygens principle, that will be a secondary. What do you say?
Wavelet.
Wavelet. Yeah. So
Hmm.
now this secondary wavelet should be isotropic, right? Like, why will it
Ha.
prefer anything?
No, you are saying that if it goes out of the behind P and then comes back or something.
Here we are basically making an assumption that the secondary wavelet knows which direction the wave is coming from, as in there is some directionality there, and the secondary wavelet that is produced
But
is not produced in all directions. It's produced only in the
Nah,
direction of the
that is
wave.
not really what I'm saying, Anirudh. What we are saying is that the effect on P will only be of that which are coming towards it.
Yeah,
Effect
so
on P.
if we
So that
allow,
there will be some which can go past P and then come towards that. In which case, I will consider, the P to be on the other side.
even if you consider an angle alpha,
Hmm,
for
hmm,
that case, suppose the point was some b in our sphere. So
hmm,
from
hmm.
b, it has to turn an angle alpha to reach the intended point p. So
Peter, no,
if
no,
it
that is it is not like that. So basically, see, you what you are doing here is all of them have a certain angular dependence with respect to that point P. Now, what I'm unless they are, so because it's going by 1 by r, essentially that distance is increasing, right? So the effect of that point on that, remember, I'm looking at only a point. I'm not looking at a area or something, just a small point, right? So that point, for the sources which are at an angle of alpha greater than 0, so those have a lesser and lesser effect. That is what we are seeing. As you increase alpha, that particular region of the wavefront has a lower effect in the point, where we are in my observation point.
yes
Okay,
sir,
so that is what we are seeing. Now,
yes sir.
if you are
So
saying that on the other,
I
uh,
mean,
that is
if
what is coming up here, because considering the distance p is let's say far away from the
hmm,
R naught sphere that we had.
ha, ha, ha,
So
ha, ha, ha.
so I don't think it's uh, the further away 1 by r factor. It's the assumption that there is no back propagation. Like if there is no back propagation, then beyond pi by 2 there won't be any
That they
this thing.
don't. I agree with what you're saying, guys, but that absolutely is not mentioned anywhere. Absolutely, it is a valid question in the
I mean,
sense that maybe what they also this thing that in the sense that alpha this thing plus some pi by 2 if you do, so it is essentially going to add a pi by 2 factor, right? So if you add another pi by 2 or pi factor or something like that, but in the sense that what I'm saying is, can we sort of say that these are symmetric? So, 2 points which are lying on the opposite sides of the circle. So if I draw a circle from that point P0, I drew just an arc, right? So if I complete the circle, okay, and I say that the points that are exactly diametrically opposite to each other, they are they are basically going to contribute the same amount or not going to be different that way. Mm,
no sir, I mean, that the contribution from the opposite side will surely be less, but it is if the distance
so
b is
basically, I see what I can say, Shubhranshu, is that Fresnel exactly did this. Okay. And as you see, Braun and Wool, for example, they just report what Fresnel. In fact, one interesting thing that they say also is that this actually solved the problem between the corpuscular theory and the wave theory also, because iska that that it's sort of uh, 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 it managed to match experiments so well that the corpuscular theory was laid to rest. But somehow, yeah, I see what you're saying, but uh,
actually, sir, the core
mm,
question is not from this Fresnel principle. Whatever Fresnel did is perfectly fine. The core question would be like that: the backward propagation is not possible, even if Huygens, according to Huygens, the theory, it is
mm,
possible. That is the core question, actually.
that he did not. I'm seeing if there are any assumptions
It is basically, I
made.
mean, plus two type question, but that
Mm.
is, I mean, it is the fact is hard from plus two level, but the exact explanation I have not got anywhere. That is the
Where
thing.
what explanation actually?
The backward propagation of, according to the Huygens
He
wavelet
doesn't
theory.
talk about it at all, right? But then there is a time issue also, right? Because if you go in time, so how will that go in the arrow of time ways, right? If you are saying that there is backward propagation, How do we know that it is? Because see, we know that time wise, time always, there is causality, and the causality is very crucial, right? So causality means
Yes.
each event has to be followed by the next. I mean, there's no backward there. So that, if I have that, then
Sir,
how will you equate the backward propagation with that?
sir, I'm reading this from the abstract of a paper that I just found on Google search.
Hmm.
So it is the abstract says Huygens principle uh, says that each point on the wavefront represents a source of a spherical waves,
Hmm.
is conceptually useful but is incomplete. The backward the backward parts of the wavelets have to be neglected ad hoc.
Hmm.
Otherwise backward waves are generated. So it's an
Hmm.
assumption
It's
basically.
an assumption, yeah. Nobody talks about it though. I mean, even Bornard Wolf does not talk about it. It's very interesting, very interesting. I didn't, yeah. You have to ignore the backward propagation ones. But then, Anirudh, don't you think time-wise we can say? I mean, what is the meaning of backward propagation? But coming towards the source.
This like basically this is a prediction of whatever the model suggests.
Ah, well, this is a
Like
consequence of the model, you can say.
consequence of the model ka
Correct.
prediction or
That is
whatever.
an interesting thing, actually.
Like
That is
what
a
Yeah,
very
Huygens says
interesting
I
that
thing.
every
think
point is a
there.
secondary source. The implications of this principle is that there will be backward propagation.
But
So
then that we
there are
neglect.
Uh,
problems in the principle itself.
Sir,
Maybe.
I remember something
Like
reading
it's
in,
incomplete
I
basically.
think, sir, I
Maybe.
think in Hecht, or I don't know which book, they had once explained why, if light is propagating in a medium through interference, they showed why in the transverse direction you won't have light, and on the backward direction through interference. You,
Interference, so you can throw out, na?
I
Interference to
forgot
very clear, right?
how
Because there's
did
a
they
phase
explain
difference of pi and all. That is too very easy. And perpendicular also, because it's perpendicular polarization, right? If you have, so unless they have the same polarization, you'll never get interference. But for just Huygens propagation per se, see, because
According to
we,
Huygens,
ha,
you get
ha, ha,
constructive
right, right.
interference in the backward direction,
Yes. So see,
as
but
much as in
Huygens does
forward.
not talk about any interference, guys. It was Fresnel who talked first about interference. Huygens just has said, as you said, that every point is a source of secondary wavelet. Okay. So वो actually नहीं बोलता है. That I am quite sure. माने Huygens, माने interference is not something that you automatically get from the Huygens principle at all. Actually, okay. The superposition thing was done by Fresnel here. That Huygens Fresnel principle, as we say. Okay. But that this is a very interesting thing. Actually, I never thought of this. Very good. Okay. Thanks, Anirudh, for this. This will be recorded, so people will be able to hear. Good. Okay, chalo. Then we'll meet next class Thursday and finish off the official part of the course.
Thank you, sir.
Yeah,
Okay.
welcome.